Hello and thank you for joining this session. I'm Zoran, coming from DeepNets, and today I'm going to talk to you about how DeepNets simplifies deep learning for Java developers. First of all, let's see what is DeepNets. It is a developer-friendly toolkit that's aiming Java developers and allows them to build advanced AI based on deep learning. It simplifies deep learning by providing rich visual tools which contains wizard and project templates. Also, it provides Java deep learning library that greatly simplifies integration of AI models into Java apps. This library is written in poor Java, but it provides greater performance. It does not rely on any external native dependencies, and that is one of the important features of this library. Before we dive deeper into how DeepNet works and how it simplifies the entire process, let's explain briefly the main workflow and some basic concepts so you can understand what's going on and what is so complex about it. What you see now on this slide, it is a typical machine learning workflow, which includes some data preparation and then splitting data into training data and test data. So the main idea of machine learning is to provide a number of examples to a machine learning algorithm, which can then tune internal parameters and become able to recognize similar data, to perform some task, which is typically classification or regression tasks. So during the model training procedure, when you create that model, you want to investigate and estimate how it is going to behave in production with some new data that it hasn't seen during the training, and that's why we use test data. So test data is the part of the original data set, and then we calculate the various evaluation metrics to see how good the model has generalized the knowledge about the data. Usually, if we are not satisfied with how good the model has generalized the training data, we perform some tuning of the model parameters, and that's a kind of debugging loop, and we repeat that process until we are satisfied with the evaluation results, and then we are ready to deploy our model. So the main point of this entire procedure is actually the training of the model, and this is another diagram which explains in more detail what's happening during the training phase. As you can see, we have a neural network, which is a kind of deep learning model, and we provide these training examples, and then on the output of the network we compare the results that we are getting as a prediction, as output of the network, with the initial truth which is provided, the real expected outputs, which are provided as target outputs. By comparing target outputs with actual outputs, we calculate the network error, and then internal mechanism of the learning algorithm, training algorithm, called optimization method, performs tuning of the model's internal parameter in order to minimize that error. So basically, deep learning is based on learning on mistakes and trying to minimize these errors. Let's now jump to the example where we see much more clear what's going on. In this example, we are going to show how to recognize Duke images. The problem that we want to solve is to say whether image contains a Duke mascot or not. And the problem with this is that there are a lot of variations. There's a lot of different types of Duke, and this makes this problem impossible to solve using a fixed set of rules, and that's the reason why we need AI. So usually images may vary in size, color, shapes, but these are all Dukes. So let's move to DeepNet's IDE, and let's run the wizard. Let's create a new project, which will be Duke project, and we'll use some prepared images for this project. Here we run a wizard which will ask us a series of questions. For example, what do we want to do? What kind of task do we want to perform? Say we want to classify images. The next thing is how many categories there are. Do we have just 2 types of images or more? Since we have 2 types of images, which is Duke and non-Duke, we are going to use so-called binary classification tasks. Now, very important step is to specify the Duke images. As I mentioned before, we have prepared images of Dukes, which we'll see later, and choose the directory with those images. Next, pre-processing phase usually includes scaling images to the same size. So let's use 64 times 64 pixels, and since we have white background, we don't want to recognize the white part of the image. We want to recognize the other colors that are available in the images, so we are going to use these options for inverting pixels. There are many more techniques that are used to prepare images, but for this example we are just going to use this pixel inversion. Next very important step is to specify a neural network architecture. So wizard helps you here by setting some parameters based on the previous answers and provided image set, but the minimum we have to specify is number of channels in convolutional layer, which means a number of features that we want to detect. Maybe we can include more, let's say 6, and number of fully connected layers, which is 1 layer and 32 in size. Usually you divide the number of input after max pooling. That's 64 divided with 2 is 32, and that's a kind of a heuristic how you estimate the number of and size numbers that are missing in these layers. Another thing is it is a classification problem. You can see this loss function has been predefined as a cross entropy, and since it is a binary classification problem, the output function used is this sigmoid function. Next, we can specify the settings for the dataset and how we are going to use our data for training. One common practice that we already mentioned is to split data into training and test set in this given ratio: 70% for training and 30% for data for testing. And as you can see, since we are going to perform a classification type of problem, this evaluation matrix is also being preset for you, so it doesn't matter if you are not familiar with what exactly do you want, which metrics to use. One good thing about this wizard is that you can use these default settings in each step, and here are some more details, so where you can control how training algorithm behaves, and there are many advanced options. but we'll use this defaults just to show you how this wizard solves all these details, and that you don't need to understand all these parameters in order to be able to successfully solve some problem. When we finish the wizard, we get a bunch of files for dataset, for network architecture, and for training. And here we see a big picture, a visual overview of what's going on, which to put it simply, we use dataset and this network architecture to run a training process and then run the evaluation. So the settings for each of these components, we have properties file with all the settings that are filled based on the answers that we provided in the wizard. So here is the network architecture, which contains a layer. Now you can see it in a JSON format, and you can also use this visual designer to modify network, to drag and drop layers, to change architecture, or to change, for example, number of convolutional channels. Let's say that we want to use 9 channels. And also, when it comes to images, let me show you that there is image dataset explorer, which can show you the images that are being used for training. So here are the images of Dukes. As you can see, many different Duke images with lots of variations. And in order to make to differentiate them from non-Duke images, we have to provide also negative examples, which is basically a number of, as you can see, images with a full color, with some white, and a number of randomized pixels. So these are Dukes, these are non-Dukes, and we are going to feed this neural network architecture with these images. So during the training procedure, there is a number of parameters which controls the way that the training algorithm is going to minimize the error, and they are all specified in this training properties file. In order to run that training, we just right click this training properties file and say run training. Now we are also going to include this visualization, which will show us how or what the network is actually doing. You'll see here how it is feeding. Let me put it a bit slower. Oh, it has also completed. It is a small data set. So just in 2 epochs, the network has reached a very high accuracy of 100%. And what it has been doing, we can repeat training. This is what each layer is doing. It feeds image, performs convolution operation on it, and then reduces the size. This is what max pooling layer is doing. And at the end, this fully connected layer performs classification. It sees what parts of images are important for recognizing specific object. Now, here in the bottom window, you can see a number of details related to the training process. For example, loading and creating image set, then creating a neural network architecture, and then every step of this training procedure. This so-called epoch is actually one training iteration, which includes pass of the entire data set, and you can see what was the error at that training iteration or epoch, and what was the accuracy. So this is very small data set, and as you can see, initially the error was 0.65, but you can see how quickly it really was decreased to 0.12 with a very high accuracy. So this is the result of evaluation. As you can see, we have missed some images. We do have one image that we have didn't classify it correctly, we didn't recognize. So this accuracy is an explanation of how often classifier is correct in total, which is actually percent of correct classification, and how often this classifier is correct when it gives positive prediction, and when it is a positive class, how often it gives a positive prediction. So these are all the details you can investigate in order to debug the recognition and this image classifier. And there is one more, even more practical tool which allows you to test the entire image set. So we can select the trained network here, okay, and you can select this training data and run test for all the images, and we can see all the images from the training set and see how they are recognized. So Duke are recognized as Duke, negative is negative, and we can turn on this only false prediction to see which images are not recognized correctly. So as you can see, this Duke with this circle around him has not been recognized as Duke. The recognition level is too low, so it's probably something should be done with the architecture or the training data. For example, we can include more layers. We can add another convolutional layer here and say we want to have let's say usually twice as previous layer, and use this, okay. And then after convolutional layer you usually put this max pooling layer. These are common practice, and let's put one more fully connected layer, 32, okay, and let's see what the results will be now. So now we are experimenting, we are tuning our model, experimenting with different architectures, and as you can see, now we have lowered, we have successfully recognized all, we don't have any more mistakes, we have accuracy 1. So this is probably overfitting because the data set is very small, but it shows this procedure. So you have the full tutorial of how to do this Duke image recognition on the DeepNet's blog on the link provided below. Once you train the network, I will show you where it is. I mentioned it. So the trained networks are serialized Java objects. So they are here, deepnetwork2.dnet, and also you can simply right click on that network and say create jar, and that's how you get the deep learning model packed in a well-known jar that you can include in your Java projects. You can also deserialize this network in your application using DeepNet's Java library, and after that, to use it for recognition, you can use Visual Recognition API, which is a standard Java API for visual recognition, which has a reference implementation using DeepNets. So basically, we are creating an image classifier for buffered images, for this type of images. We are loading image files into buffered image from Java class, and here we are instantiating image classifier network using the trained convolutional neural network. To classify the image, we just invoke the classify method and provide image to classify, and we get the results as a map of image labels and corresponding probabilities. After that, we can print it or do whatever we want to do with it. The entire training procedure that you have seen can be also performed in Java code for those who prefer that way, but as I mentioned, that approach requires more understanding on the machine learning workflows and some experience, but it is possible and fairly simple. In this code segment, you can see how to load image set of some size from some training file, which is basically a list of images, and by the way, these files can be automatically created for you. This piece of code shows you how to create a convolutional neural network architecture using a builder. Again, we are specifying dimensions of the image in input layer, and then adding convolutional layers, max pooling layers, fully connected layers, and specifying what type of loss function we want an activation function to use. Now, if you are just starting with deep learning, probably many of those settings are very confusing for you. So that's how this tool helps you by eliminating some of these settings and helping you to provide some settings which are considered to be a best practice for specific types of problems. In this code segment, you can see how the training procedure is performed by getting a trainer from the convolutional network using getTrainer method, and then setting error threshold by using method setMaxError, and setting parameter which is very important for training, which is the learning rate, which determines the step size or the part of the error that is going to be used for modifying internal network parameters. The call to train method with the training set finally invokes the training. The full code example of this training for Duke set is available on GitHub on the provided link. So when we compare DeepNets to the other Java deep learning engines, some of the main points that I would say strong points of DeepNets is that it is more user-friendly for Java developers, and it provides Java flavored API. Some of the others, like TensorFlow, is more like Python flavor, and it might be confusing. Lots of low-level data structures that Java developers are not familiar with. Also, Deep Learning for J has many options, but it is very complex for beginners. And DJL is interesting option because it wraps basically other frameworks and provide Java API, but it also has native dependencies, and it can be different to run on smaller devices, and to integrate on a number of different devices. Also, it is worth mentioning that DeepNets runs only on CPU, and despite of that, it has a very good performance. But it cannot do real-time video detection, but for a medium-sized problem with reasonable number of images, it can provide very good results. At the moment, DeepNets is being used by a number of developers, starting from beginner Java developers who are using it for game development, through Android game developers, and up to advanced scientific research. It is interesting to mention that a 14-year-old boy, after learning Java during a lockdown, has used DeepNets to create AI for his Sudoku game. So this definitely shows that you don't need to have PhD in AI to be able to use deep learning in Java. Another use case for visual chess recognition application performs recognition of chess pieces on the screen, and it is, as mentioned, working as an Android app. And for this use case, DeepNets had a very important advantage over other alternatives because it was much smaller and 60 times smaller because it did not have native dependencies. At University of Minnesota, their lab for computational chemistry had a Java application which was managing the experiment related to drug discovery, and it was very easy to integrate DeepNets, and thanks to using deep learning methods, they have significantly lowered the time and the number of experiments, and also created a cheaper process. At the moment, we do have information that DeepNets is being used at Jefferson Institute for some advanced physics and particle research, and we expect the research to become public soon. Also, there is a community edition of DeepNets. It is an open source which provides all of the main features that the DeepNets has, but if you need higher performance and better accuracy and some professional support, then it is recommended that you use Professional Edition. As I mentioned, there is ongoing work on visual recognition API as an official Java technology standard, and the reference implementation of VisuRec API is based on DeepNets Community Edition. The technologies that DeepNets is using is it runs on Java 8 or higher. The IDE is being built on top of Apache NetBeans 12.6, and optional recommended JVM to use is a Zool build of OpenJDK. If you would like to get started with DeepNets, just follow these two links. It is free for download and free for development, and you have a step-by-step getting started tutorial to quickly help you to start. You can also contact us and provide information about your project and qualify to get a free low volume production licenses. Thank you for listening to this presentation, and please let me know if you have any questions.